All right. All right, we'll start off with how do you think electricity comes to your homes? Yep, Nathan?
I think so they basically make the energy using nuclear power or some other source, and they transfer it through wires. And since they don't want it to touch the ground, which is gonna just let the electricity flow out, they put it high, and then it reaches to each single wire probably leads to the like city wires that are wooden, and then those could split and then reach to each house.
Very good. That's pretty much the gist of it. So there's a pathway with where the electricity travels. It starts from the generating stations. Like you said, there is nuclear power, and then there's different ways that electricity is generated. Then it goes through these towers and wires called electrical grids. These are all steel towers, and then it goes to boxes. So there's common electric boxes, and then it comes to your homes so that you can plug something into the wall and use electricity. So we'll talk a little bit more about what are electric charges. For that, we'll have to learn a little bit more about the structure of an atom. So does anyone know what an atom is? Tong unmuted himself. Tong, did you want to answer?
I don't know much about atoms, but all I know about them is if you split them, they will explode.
Okay, let's hear another one too. Nathan? Yep.
So an atom is a combination of proton, neutrons, and electrons. Protons have a positive charge, electrons have a negative charge, and neutrons have no charge. And every single stable atom has an even amount of protons and neutrons, and unstable ones have an unstable amount of protons and neutrons.
Very good. That's a quite an in-depth definition. So I just want to talk about the rings on the outside because that's mainly where we see transfer of charges. Those are called electron shells or orbits. And in general, that area around the nucleus, which holds the positive and negative or positive and neutral charge, is called the electron cloud. So when these charges they move around, that's when electricity is formed or charges are made. So look at the first picture, right? On the top left. How many electrons do you see on either side? The electrons are the little blue ones. Yep, Nathan?
12?
Yeah, so you see
I
three.
think
Hmm?
whatever.
Yep, on the left-hand side, you see 3 electrons. And then on the right-hand side, the atom on the right, you see 3, 4, 5, 6, 7, 8, 9 electrons. So what happens in the second picture between the two atoms? Yeah?
Me?
Yeah, Nathan, go ahead.
I want to let Sophia have a turn.
Sorry? Okay.
I'm gonna let Sophia have a turn.
Oh, is there someone else there?
Me?
Why do I see? Oh, okay, now I see. I couldn't see everyone at first.
I saw Sophia raising her hand.
Oh, okay.
Okay, so there's this electrons that's like spinning through both of the atoms.
Right? Okay, so the electrons are switching from one to the other, right? The charge is moving. So how many charges just moved from the one on the left to the right?
One.
Yeah, good, one. So one electron moved from the left atom to the right atom, right? So now what will happen to the charge? What happens to the atom on the left with only 2 electrons? Okay, Nathan?
I kind of feel, I don't know, I forgot this part, but I think it becomes positively charged or negatively charged.
You're right. It becomes positively charged because when it loses an electron, it's losing a negative charge and it becomes positive. But the atom on the right-hand side gained an electron, so it becomes
Negative.
negatively charged. Good. So the atom on the left has +1 charge, and the one on the right has a -1 charge. Did everyone get that? Okay. All right. So we'll talk a little bit more about different types of charges, right? If they're the same charge, they're the like charge, do they come close to each other or do they go apart from each other? All right. So like charges, they always repel each other, meaning that if there are two of the same charge, they move away. If there are two of the different charges, they come together, like how we say opposites attract, right? So unlike charges attract. This is a picture of two positive charges on the top right. They're actually moving away from each other. And then the one on the bottom with the two negative charges, they're moving. Yep, Sophia?
It's kind of like magnets, and I think magnets have this magnetic field, and then magnetic fields has something to do with atoms.
True, it is the movement of these charges that causes magnetic energy too. Electricity also has magnetism around it. Very good. And then the one in the middle, they're two different charges, right? A positive and a negative, so they repel each other. So what happens, do you think, when I have a plastic comb and I run it through my hair continuously, like again and again? What do you think happens to the charges? Yep, Nathan?
It's picking up electrons.
Good, very good. So what do you think will happen to your hair? What's left in your hair? What charge? Sophia?
The positive ones.
Good, very good. So now your hair will be left with a lot of positive charges, right? What happens now when you put a balloon next to your hair?
Your hair will float up.
Yeah, it'll float up. So it'll look something like this, right? Because all the positive charges are putting your hair apart from each other, and then the balloon has lots of negative charges. So your hair will stick to the balloon. Very good. Right. So another example is when you're doing laundry, right? You have a lot of clothes in your dryer, but when your dryer comes out, you see how like this boy is holding all the clothes sticking together? So why do you think that happens? Okay, so yep, Sophia.
In the dryer, it rubs each other, and then some clothes have positive or negative charges, and then they rub against each other. They kind of stick together.
Yeah, that's good. So what happens is there's a movement of charges. So there's some negative charges that move to other clothing and some positive charges that move to negative ones, right? And then, oh, someone's
Um,
one sec.
I have a question.
Yeah.
Before the one for the balloon thing, I I don't know why the balloon is full of negative charges.
Why is the balloon filled with negative charges?
Yes.
So it's not that it only has negative charges, but because your hair has so many positive charges in it, as soon as the balloon comes near it, all the negative ones align next to the side that your head is against, and then the hairs stick. Very good question.
Okay.
All right. So the movement of charges in the laundry, right? So all the clothes, there's movement of charges. The next one is, like Sophia had said, some of the clothing develop a negative charge and the other ones have more of a positive charge. So then they start sticking together inside the dryer. But there are some clothing that don't stick and then they just fall down. Why do you think that is? Nathan?
Because they're positive, both positive charges.
Good. They can be both positive charges or they're just simply neutral. Even after the rubbing, they just seem to be neutral. Good. Um, okay. So from all of the examples we've seen, what does this transfer of charges and like this kind of a scenario where things stick together, what is that called? What kind of electricity is it? Okay, I'll give you this one. This is actually, oh, for some reason it's not working. Static electricity. So that means that the charges are stationary, they don't move. So static electricity happens when there's a large buildup of charges in one object, right? So that's why when you take a balloon and you rub it on your hair, there's a transfer of your electrons to the balloon. So it starts building up in the balloon. Now, when you move that balloon towards the wall, what happens to all the charges in the wall? Does anyone want to guess? So I'm saying that a lot of negative charge for me is going into the balloon.
It becomes the walls. Most of the negatives sides go to the closest part of the balloon.
Yeah, so because the
I've tried
balloon,
that before, and it actually like sticks to it before it falls down.
yeah, it does. Because momentarily the balloon has so much negative charge that it attracts all the positive charges on the wall. So it sort of looks like this. And that's why the balloon sticks to the wall. But you can see the other balloon next to it, both of them, when they have positive charges, they start repelling each other. Okay, let's do a quick math exercise. You see there are some missing squares, right? Anybody raise their hand and you can guess what the final charge on the object is. Like we'll start with the first one, right? The original charge on the object is positive 300. It gains 270 electrons. So what is the final charge? Sophia?
570.
Okay, let's try that one again. If you're gaining electrons, what kind of a charge are you gaining?
Negative.
Negative charge. So if you add positive 300 and negative 270, what do you get?
Oh,
30.
30.
Yeah, 30. Very good.
Kind of a weak charge.
Yeah, kind of a weak charge, isn't it? So let me just write that one down here.
Nice, you can annotate.
Yeah, I'll just write it down so we can see. And let's put the sign in front of it. Should it be a negative sign or a positive sign?
Positive.
Positive. Good. Because this is actually negative 270, gaining electrons. Now let's try the second one. You have negative 300 to start with, and you're losing 525. Nathan, yeah?
225 plus 225.
225? So if something is losing an electron, right?
It's
It's gaining.
gaining positive charge.
Yeah. So now what do we have to do? We have to add, right? This becomes plus 525, right?
Hmm?
And then you have to add that to this. What do you
Yes.
get? Yeah, Sophia?
Positive 225.
Yes, good. Positive 225. Okay, someone else will try the third one. So now they've given us the final charge on the object and the original charge, and we have to see how many electrons were either gained or lost.
Maybe losing 220, 230.
Yeah, no,
Gaining.
gaining. Yeah, correct, Catherine. That's good. So because you gain 230 electrons, that means that you're adding negative 230 to negative 270. Very good. All right. So we'll learn a bit more about electrostatic discharge, right? We already know that when charges accumulate, it's static electricity, right? And when another object with a different charge comes close to it, those charges move over. For example, when you're walking on the carpet, right? And you're like really rubbing your feet against the carpet, the electrons will jump from the carpet to you, right? But you also have a lot of electrons in your body, right? Human body is more electronegative than it is positive because we have so much water in our body. So when you have more electrons, the excess electrons that come in are a little bit repelled and they stay on the outer surface of your body. So as soon as you go and touch something like a metal handle, have you guys ever touched a doorknob and then you get a big shock?
I touched
Mm,
the slide before and I got
Yeah.
I call it a sparkle.
Yeah, a sparkle. You get that, right? It's because your
sometimes
body,
it's like if you rub it enough intentionally, it's like very powerful.
yeah, if you do it on purpose, it becomes bigger because you're just accumulating a lot of charges and going
And
and
it's like
touching
the
another.
more and more and more and more until it's like literally as powerful as a charger.
Exactly, yeah. So then so what's happening there is an electrostatic discharge, right? Whatever extra charges are on your hand is jumping onto the other object that you touch, and then it makes a spark because it's a quick transfer of excess charge. Okay, so in this photo, like Catherine had mentioned, going down a slide sometimes gives you that, right? What do you think? What kind of charges are transferring here? Yep, Sophia?
I think uh negative and positive.
That's right. There's always going to be a bit of both, but just because we're a little bit more electronegative, when you slide down, I think maybe some of our electrons are getting onto the slide, and so our hair starts repelling each other because they become positive. All right, the next thing we're going to learn about is lightning. We've only seen so far very small discharge, right? Now we're going to look at a big electrostatic discharge. The same
Imagine
thing. Hmm?
imagine if someone rubbed his feet so much that when he touched the doorknob it made lightning.
Oh my god, they would have to be a very big seat and a very big person to make that much electricity. But anyways, the same concept that you see in a discharge with your finger and like maybe a doorknob is the same thing that happens between the sky and the ground when lightning occurs. So what happens is in a during a stormy day, right? There's lots of raindrops and hail or ice particles. They start rubbing against each other in the cloud, and all the charges from one move to the other. There's like a small shift in charges to either side of the cloud. Sometimes on the bottom they'll be more negative, and on the top they'll be positive, right? But at the same time, the ground is also differently charged. Some parts of your ground is negative and some parts of your ground is positive. So what happens when there's enough difference in charge between the top, the sky, and the ground? It's called a potential difference, right? When there's a huge potential difference, there's a lightning that strikes from the cloud down to the ground where there's an opposite charge. Okay. So these lightning bolts, right? They can move between a cloud to different parts in the air, or they can move between the clouds to the ground, or between one cloud to another cloud. Did you actually know that like the heat that's produced from lightning is even sometimes hotter than the outside of the sun? So it gets really hot. Yeah, Nathan?
What about lightning balls?
Lightning bolts or
Balls. I've heard
what
of them.
lightning balls
Yes, they're like electric charges, balls of electricity that float around.
up in the clouds or do they ever come down?
Sometimes they come down. It's pretty rare.
Oh wow, that's something new. I've never heard of those. That'd be pretty cool to see, if you see a video of it. So this is a picture of what the different charges would look like in clouds, right? So sometimes there's more positive, sometimes there's negative, and then you see the ground at the bottom also has different charges. So when there's a potential difference, right? So the top of the cloud has positive and the ground has negative, then a lightning bolt strikes from the top of the cloud to the ground. So that's how electricity or like lightning bolts are formed. All right. So there are some tips that I'd like to give when, you see lightning outside or it's a thunderstorm. You should always stay inside when you see lightning. And you have to make sure to turn off your electrical appliances if there's continuous lightning bolts, then you have to stay away from open windows or like close them. And if you're outside, a good tip is to be inside of a car with a metal top. Why do you think it's better to be in a car with a metal top?
Because the metal is a good conductor of lightning.
That's good, yeah, because it's a good conductor and it distributes the charge out. So you have to watch the weather forecast and see what the weather's going to be and
And
plan
it
ahead
said
of
there
time.
would be a
Unless the
thunderstorm.
whole car is like made of iron.
What do you, oh, even the inside, you mean?
Yes, like the seats and all.
There, that would be bad. Then everything will just conduct right into you.
Um, um, uh, right now, like we just got notification that there will be a thunderstorm or something
Oh
here.
wow.
A thunderstorm, what, tonight?
It might
Yeah,
thunderstorm,
yeah.
but I don't think so. It's
For me, it already passed.
For me, it's
no,
starting
there's no
to.
thunderstorming today. I didn't see any thunderstorms, though I did hear that
Shall we get to know where we live?
Yeah, where do you guys live?
New Jersey.
New Jersey.
Chicago.
It
Wow.
had a new. It just had a notification thingy. I have no idea why.
Oh, okay. I'm actually in Toronto, Canada. So for me, it's
Toronto.
nice and. Mm-hmm.
Oh wow, I got lots of classmates or friends that came from Chicago.
Really?
Yeah.
Like recently?
Uh, yeah, they're like still in Toronto.
Nice. All right. Let's see. Okay, so next thing we're going to learn about is flowing charges. All this time we've only been looking at static charges, right? What do you think those little blue dots are inside of the copper wire?
Electron.
Yeah, good. They're electrons. So what is that thing that's surrounding the copper wire? It's that red and green area. Anybody want to guess what it's called? I mean, you don't have to say the material, Sophia.
Well, I know its uses. It prevents electricity from getting out, just in case.
Uh-huh.
I think it's made out of part called or plastic or something like that. I forgot what it's called, but
Okay. And anyone else want Nathan?
Non-conductors.
Good. Non-conductors, or they're also called insulators, right? So any material that prevents the electric charges from flowing or it blocks it, they're called insulators. Right? They resist the flow of current. So what exactly do the blue dots, right? They're moving in a certain direction through the copper wire. What is that flow called? Yep, Nathan.
Electric charge.
It's the flow of charges. What is the flow of
Oh.
the charge called?
Hmm.
I'll give you a guess. It's something that you have in your house, and you when you plug your appliances or devices into the wall, you're getting.
I actually don't know this. I forgot.
It's a very common word. Current, electric current.
Oh.
Yeah, the movement.
oh,
Yeah. So the movement of charge is electric current. All right, so we'll look at different forms of energy now. We already talked a little bit about
Yay,
this.
batteries.
We talked a little bit about this before. So we already spoke about why do we use current, right? Does anyone want to give me an example of why we use current? Yep, Nathan?
To get energy from one place to another pretty fast.
Yep, good. And where it comes from, Nathan had already said, it comes from different kinds of energy stations. Does anyone want to name a type of energy station? Sophia?
uh, batteries, solar panels, uh,
Solar panels, yeah.
these wind thingies,
Yep. Wind turbines?
and these windmills.
Windmill, okay. So wind turbines are good. Nathan, yeah?
Geothermal energy.
Geothermal, okay, good. Um, so how is that obtained? Like, what's the way that you get, like, what is geothermal?
Um. So it's It's energy stored in the earth and it takes it out.
Okay, good. So
And it's
another
also nuclear.
nuclear, very good. So another one is fossil fuels. You know, when you burn coal or gas and stuff, the kind of energy you get from that. Very good. It's all good examples. So what is the difference in the type of energy you get from a battery compared to, say, wind energy? Catherine, did you?
I wasn't raising my hand.
Oh, okay, my bad. Okay, Nathan?
In the windmill you're making energy. In the battery there's already energy.
Very good. So it's always a transfer of one type of energy to another. So in a battery, we have lots of chemicals, right? We're converting chemical energy into electrical energy. But in a windmill, we're converting wind energy into mechanical energy, which is the rotating of the turbine. And then the rotating turbine converts the energy into electrical energy. Okay, so what kind of items in your house do you use a battery for? Sophia?
Electric car, remote control car.
Yep.
This like many toys that can move, they all use batteries.
Yeah, very good. And what do you use with wires instead? I think you have more of those at home. Yeah, Nathan?
Electronic iPads, phones,
Mhm.
computers, iPods.
Yeah, good. So what do you know those towers you see, right, that form the electric grids? It's always a good idea not to play around them because a lot of radiation comes from it in terms of magnetic waves because electricity flows through it, right? So also don't dig underneath it because there's lots of wiring that's underneath. So
The
always
most closest I've been is like 3 miles.
3 miles?
Yes.
Oh, wow. But 3 miles is still far away, so that's good. You're not anywhere near it.
Maybe like 2.5.
Yeah. Okay. All right. So the next thing is we're just going to go through a few questions to review the material we just learned. One person can answer each question. So the first one is each of the three types of particles that make up atoms have different charges. The first one's listed there. Protons have positive. Can you name the other two? Does anyone else want to give it a try for this one? Okay. Sophia?
Electron negative.
Electrons negative. And what's the third one? Oh, Nathan? I thought Sophia was going to answer. Yeah.
Neutrons have no charge at all.
Neutrons are neutral. Good. Okay, so B. Who wants to answer the next one? Atoms can gain or lose electrons, right? What is the definition of static electricity? Yep, Sophia?
Moving around.
No, static. What does static mean?
I
Static means it's stationary, doesn't move, right? So, okay, Nathan, what's the definition of static electricity?
Static electricity is electricity that doesn't move around and stays put until something affects it, like an electrical transition.
Good. It's a buildup of charge until something else comes close to it and then it moves around. All right, so like charges repel, right? When objects interact with each other. What is the other statement that's contradictory to that?
I'm giving everyone else a chance.
If like charges repel, what do unlike charges do?
There's like, maybe there's only like one answer, probably like two answers.
stick together.
Yeah, Sophia, yeah?
Stick together.
Yeah, they attract. Oh, there's no answers written here, but they attract each other, okay? All right, so the next question. There's going to be a lot of review questions, so we know that we learned our stuff well. Electrostatic discharge. Who can define this? Yep, Nathan, give it a shot.
Um, when something loses its electrons and gives it to another item.
Okay, close enough.
Something like that.
Yeah, the jumping of electrons. Good. So the first one, the example given there is you're getting shocked when you're walking across a rug, right? Like rubbing your feet. What's another example we saw? Yep, Sophia?
Laundry thingy,
What was that?
the dryer, the dryer and the clothes thingy, and the comb and the hair thingy.
Yeah, very good. So the next one is who can define what electric current is? Okay. Anyone else want to give it a try? Just from like, you don't have to give a proper definition. Just try to explain what you think it is. No? Okay, we'll get Nathan to say this one.
Electrical current is electricity that's moving.
Yeah, charges that flow. Good. And what were the sources that we saw? One, they've already given here generating stations. So what's another source? Sophia?
Batteries, windmills, this, yeah.
Good. Yep, Nathan?
Geothermal, water power, heat, maybe, fossil
Yep.
fuels, nuclear, and like,
If they just move a turbine by themselves?
yes.
Yeah, that works. All right, so we're going to do a little game here. You guys tell me the answers and I'll write it down. So the first one is two positive charges. What do they do to each other? I think Tong had written this in the chat box, so I'm just going to write it down. Oh, why is that working?
Repel.
Oh, attract. Positive charges, two positive, repel. Okay, he said attract. I'll just write this one. Repel. Okay, then a positive charge and a negative charge, what happens between them? Okay, Nathan? Or Sophia?
Attract.
Yeah.
Okay. Attract, good. And then how about the buildup of electric charge in an object? Okay, Nathan?
Static electricity.
Static, good. And then the flow of charges along the path is electric?
I'm just gonna let someone else do this.
Me too.
Does anyone else want to answer? We have a ton of games, so it'll be fun. All right. I'm gonna answer this one. Electric current. Okay, and a proton has what kind of a charge? Pro. Think about pro meaning
Positive.
positive. Okay. Positive.
A neutron is, I forgot.
Neutral.
Oh yeah. I remember it's new something.
So an electron is, I think you guys know it, but not everyone wants to say it. It's fine. Negative. And electricity produced at a generating station. Good. Now let's try to find these real quick.
Can we annotate?
Yeah, can you?
No.
Yeah.
You need to like. You need
Oh,
to
I
like.
have to give you permission to do it, right?
Yeah.
Okay. Um, are you guys able to see it? You're not able to see the annotate button, right?
No.
We're not. We can't see it.
Okay, hold on. Enable annotation. Okay, did it. So whoever wants to go ahead.
Can we just go
Okay,
ahead?
Nathan, do the first one, and then after you're done, Sophia will do the second one. Okay, current. And then Sophia, you find one. Station. Good. And someone else want to find repel? Oh, I actually spelled it wrong. It only has one L. You'll be able to find it. Good. And then someone else find attract. Good. Attract. And then the next one is
Stop covering it up.
positive.
I found negative.
Good. Positive. And then let's do neutral. Neutral. Okay. And then we have, so what's the last one? Did we get everything? 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. There should be one more.
Negative.
Oh, we found negative up there.
Station?
We
No,
found that.
is it there?
We found neutral. We found
Did we find static?
static. No, we didn't find static.
Oh
Oh,
my.
that's one.
Oh, it's so covered up.
Static. Okay, good. So now with all the leftover letters, right? You see the bottom there? You have to guess the riddle, right? So put whatever letters are remaining in the riddle in order. So start with F, R.
R. F. R.
What? How do you do it in order?
What?
Find the letters you didn't circle in the words.
Oh, frightening lightning. From
Oh, that's what it is.
top
Yeah.
to
What?
bottom.
There's tight.
Frightening lightning. A very scary electrostatic discharge.
There's tight or something like that. What the heck?
Are you guys writing with a pen or your fingers?
Pen.
Pen, okay.
What?
Isosceles triangle.
All right, very good. Thank you, Tong, for writing the answer.
That one that you just wrote was
Okay, now we'll go to the next one.
Neutron stars have to do something with neutrons.
What is this? How do I remove it?
Sorry, I'll erase mine.
Ta-da!
Wait, I can't erase mine.
Just click clear.
Yeah.
But I can't.
Just clear. You can just clear.
it's because
Yeah.
you disabled annotation.
Oh, so you have to clear it by yourself?
No, you can just click clear and then it has options and it clear all.
Okay.
Yeah.
Okay, good.
Dee-dee.
All right. So this, we've already done this one. I think we're pretty thorough with this. Where are the particles found in the atom? That's a good question, right? So where are the protons and neutrons found? Anybody else want to answer this? Are they found outside or inside? Okay, Sophia?
Um, the neutrons, and the protons.
Yep.
Are they called like that? They're together in a ball at the center. It just cancels out, and then the electron circles around it. It's pretty. It's really pretty. Like,
Yeah. Good job. So what is that ball in the middle called collectively?
The nucleus.
Very good.
Nucleus is also the definition for the center of a cell.
A cell. Yeah. Okay, so a quick explanation on why the balloons are sticking. I think we all know now, right?
Static electricity, and that's a lot of hair.
Yeah, okay. Very good. Um, okay, so 3 ways you can use electric current. Let's get someone else to answer. And
Char-
this could have
Anyone?
anyone want to answer? Jennifer? No? Okay, that's fine. Okay, Nathan?
Charging your phone, charging your iPad, charging your computer.
Okay, good. All right, so this is a flow chart, right? Let's fill in the blanks. So what happens to these 2 pieces of clothing?
Rub.
They
Yep.
rub against each other and then they attract
Okay, and then the electrons move from the wool to the
to the cotton strip.
cotton. Okay, and then the 2 pieces of clothing have what charge?
Stick.
No, like what kind of charge?
Repel. Oh,
Have
negative.
Is it unlike or like charges?
Like.
If they rub together, would they end up having like charges?
No, different charges.
Unlike charges, good. And then once they have the unlike charges, what happens to both of them?
They attract
They attract each other. Very
and
good.
become so hard that you can't separate them.
Yeah. All right. And anyone want to explain what's happening in this picture here? Catherine, do you have your hand up?
Mate,
Uh-huh.
yeah. I think it's because trees are easily get hit by lightning.
Yeah, they do. So when the charges develop, because the tree has a different charge. Okay, someone else want to explain it too?
I can.
All right, Tom, go ahead.
Lightning usually hits high places, so the tree is very high and it's more likely to get struck by lightning. That's
Yeah.
why in a thunderstorm you should avoid trees in case they fall on you. Maybe
Yep.
tomorrow your mom could have fried human pancakes by people that are crushed down from trees.
Oh my God, that was very morbid, but thank you. That's a good explanation. Yep, Nathan?
So there are lots of charges in the clouds. So at the top, they're normally positive. At the bottom, they're normally electrons. Since the ground also has positive and negative, so the top is more has more like positive probably.
Mm-hmm.
So the tree is also with the ground, so it also has a more positive charge,
Yeah.
and it's high enough so that lightning strikes it and transferring electrons to the positive tree.
Yep. Very good.
Probably until it's zero.
Yeah,
It's
it's probably
like all neutrons
yeah, and at that point the tree probably would burn.
be gone in ashes.
All right, let's draw a line. I'm gonna draw the line, and you guys just tell me where I should draw it. So where would the battery go to?
The battery?
Oh, okay, it's like the exact same word. Oh,
What?
what happened there? Oh, it's because it's not annotated. All right, so this is the battery. And what is this one here?
Static electricity.
Actually, that's good, but what's exactly
Oh,
happening?
discharge.
Yeah. And what's this one?
Static electricity.
Yeah. And then this one?
Electric currents. That's
Very
obvious because it's the last one. I don't
Yeah.
even need signs for that.
All right. So someone give me some safety tips for the group. We are at a park and we're playing soccer. You hear thunder that's pretty far away, right? What should you do? Sophia?
You should go into a nearby building or go into your car. It has a metal top. And then the one thing that's not safe to do is to run under one single tree in the middle of a park, because if the lightning struck the tree down, you're
Mhm.
gonna be hurt too.
Yeah, good. Nathan, you want to add to that?
If it starts raining and there's shelter, try to get and the shelters and make sure the shelter's not too tall. Try going in or asking the owner if you can go in. If it starts raining and there's no light like buildings nearby or shelters, you should try laying flat on the ground so lightning doesn't find you.
Exactly. All very good tips. Anyone else want to add? No? Okay, I think we've covered it. All right, so what are some ways we can prevent our clothes from sticking together?
Wax them.
Wax them. What, you mean like put cream on them?
Oh
Wax.
gosh,
Put the wax, like
that's
candle
gonna
wax
be
on them.
so messy.
Yeah, like we get all over the place. But what's another, like we use dryer sheets, right? You've seen bounce sheets and stuff or Febreze sheets that you throw into the dryer so that they don't stick, right? But what's,
Maybe try putting some thick balls so it smashes
Oh,
them up.
yeah, Sophia?
I have an idea. You put one shirt here, and then you put a layer maybe of some kind of metal, because plastic doesn't work in a dryer. Another clothes, and you go on, and then stick it into the oven.
That is actually quite a good idea.
That's a good idea,
How about
actually.
you just bake the clothes?
Okay, baked
Uh,
clothes, it could be too much heat where like it ends up burning. But a good idea, like Sophia said, aluminum foil, right? You can
Yeah.
make balls of aluminum foil and throw it into your dryer, and then it'll
Maybe
prevent.
you can try using a balloon to decharge
well,
the clothes so that it
you're
has
gonna
no positive
your dryer.
or neutral or a negative charge.
Maybe that'll work. I want you to try that and learn.
It's just I have a device to actually measure electricity.
Oh,
I'm
cool.
serious. I can get it right now. It's like across
Well,
this
if you
place.
put a balloon in a dryer, you're gonna break your dryer, and in the middle of nowhere, you're gonna hear a pop.
Maybe. All right, so let's look at these balloons, right? So I'm just gonna draw them here a little bit. Oh my goodness,
Oh my.
zoomed in. Why is that doing that?
Oh my.
Sometimes the annotate doesn't work. That's why. Okay, good.
That's mean of the annotation.
Okay. So we have the two balloons, right? And the first picture, you see all these positive charges here. And if the balloons are like they're coming towards each other, right? What do you think is on this balloon?
Negative.
Good.
Negative.
Good. So how about the second picture? You have a bunch of negative charges, and then they're going like this away.
Negative.
Negative.
Good. All right. The next thing we're going to talk
Yay!
about is
Robot.
circuits, okay? When you look at this picture, it's an X-ray image of a robot.
What about the resistor?
Yeah, there are resistors in it actually, the big blocky things, but what do you actually see in this X-ray image?
I see lots and lots of wires,
Good. So
lots of metal and stuff.
Some engine.
And I can practically see it kind of like made out of plastic or something.
it could be.
An engine. Some engines and some screwdrivers.
Yeah, there seems to be
Screws.
screws. Yeah, there seem to be screws and some engines, and most of it is circuit, right? Like a circuit or wiring. So that's what we're going to learn about next. So you see this worker